Today we have put a difficult task in front of three of us to describe and try to explain data interoperability in the context of smart grids. And today our webinar will merge three parts. In the first part, Professor Dr. Matej Zajc at the Faculty of Electrical Engineering in Ljubljana will present this data interoperability as a fundamental concept for smart grids. Then I will talk about this basic concept to understand SIM, Common Information Model, through very, very simple example. And at the end, we have grand finale with our junior researcher at EIMV. She recently received her MSc in this domain. Amila Dervishevic will talk about how this graph databases fits into smart grids, data interoperability, and SIM, using this as a basic concept. So today we will try to start with the data interoperability and go through SIM and correlate this with all the knowledge information stored in the graph databases, and at the end come again and show this interoperability as a crucial component to extract some knowledge from different sources in the smart grid. So, Matej, the floor is yours.
Yeah, thank you. Dear colleagues, it's my pleasure to be part of this webinar today, and thank you for joining us. In this first part out of three, we will overview some issues related with data interoperability. This is some sort of introduction, some sort of warming up for the second and the third part, which will be more practically oriented. So let's start. The smart grid vision is to become system of interoperable systems, and different systems must be able to exchange information in support of secure, efficient, reliable operations of the grid. Interoperability must be solved on all levels, from local to global level. If we look at some current challenges related to data exchange, we could maybe identify some as integration of renewables, active participation of prosumers, and maybe on the other side also pervasive use of data science. There are many stakeholders in a smart grid with diverse needs. They use different technologies and data processing and storage. As a result, they have a problem of combining multiple heterogeneous data sources. The goal is to exchange data in an optimal way between systems in a company, between companies, and down to simple machine-to-machine communications. There is high demand for interoperability at all levels. It is crucial that for future services, information is not shared only in a company, but with all stakeholders who need it. So let us investigate the definition of interoperability. In the context of smart grids, interoperability is related to the platforms that enable machine-to-machine communications, data formats with well-defined syntax, and semantics as a common understanding of the content in the exchange messages. Interoperability allows system operators and other stakeholders to integrate various devices and software tools in their business processes. Today, integrations still require experts to configure systems, interpret data, etc. We understand that manual configuration is the main obstacle for successful digitalization. The goal should be to have automatic data exchange. Smart grid interoperability should be considered from the 5 interoperability layers provided by Smart Grid Architecture Model, SGAM. SGAM framework is utilized for design of use cases which represent technology-agnostic viewpoints of interoperability. SGAM has three-dimensional model with smart grid plane in 2 dimensions that consist of zones and domains. And on a vertical axis, we have 5 interoperability layers, where in the scope of today's webinar, we will focus on communication and information technologies. Communication. The communication layer covers communication protocols and therefore deals with communication interoperability, and information layer deals with data models and therefore deals with data interoperability. Let's have a look into data interoperability a little further. We can identify data interoperability as syntactic interoperability if we are concerned about data formats and message structure, and semantic interoperability if we are concerned with automatic interpretation of exchanged information. And this is the focus of this webinar. We will see that both sides need to have a common information model to understand the information in exchanged messages. Semantic interoperability introduces metadata, which provides additional information about the exchange data, which ensures information to be correctly interpreted, precisely described, and uniquely identified. And so we come to common information model. In future power system, IEC SIM is recognized as a key enabler for interoperability at the information layer. It is widely accepted and most comprehensive semantic model and ontology of the electric power system. This is the focus of the second part of this webinar, where we will learn in more detail about SIM and how we use it. Many different applications inside one or several organizations need to communicate with each other while using different data formats and communication protocols, for example. As mentioned earlier, we must overcome point-to-point integration and implement ICT architecture as a service-oriented architecture. Such example is presented in the figure, where SIM-based integration is achieved by introduction of message bus. This is a middleware service that allows applications to communicate using predefined message format. This message bus is denoted as SIM Enterprise Service Bus, ESB, in which SIM provides semantic model for data exchange between various applications. Previously, we mentioned scalability as a crucial point for a large-scale digitalization of power domain. And IoT architecture concept is designed for scalability. So the idea of substituting traditional client-server architecture with publish-subscribe concept allows others, also known as subscribers, to receive data without publishers' knowledge. This enables companies to expose data to all interested parties. In case of previously mentioned Enterprise Service Bus, publish-subscribe model is available, so it's already implemented. As a conclusion of this first part, let's overview presented information on a simple example. Let's say we have two systems, system A, a billing system, and a system B, core data system, each having data stored in a database and in different formats. Integration is achieved by SIM Enterprise Service Bus, ESB, in which SIM provides semantic model, as we learned earlier, for data exchange between various applications using predefined message format. We can see this demonstrated as a table at the bottom of the figure. As both systems are using the same semantic model, they can exchange the information. Therefore, we conclude that shared semantic models are foundation for interoperability in smart grids. This will be further investigated in the second part, which is titled Basic Concept for Understanding SIM, which will be presented by Nermin. Thank you for now.
Thank you, Matej. In the next part, I was thinking how to present such complex and evolving stuff, such as common information model. So after discussion, I decided to focus on the grid model and to use very, very simple topology. So we have here generator, we have bus bar, we have some line, another bus bar, and we have some load. And then we say, okay, we would like to use SIM to model this very simple topology. And we come to the SIM, that is common information model. And this slide is put only just to see what you usually see, what you usually find when you start working in this, to get some information. So we're talking about first thing, which is information model. It means it's only a model. It describes an object from the real world. In our case, for instance, power system component. And in common, it means that systems or applications agree to use this type of model, and that is standardized. Okay, what is another advantage that you will find about SIM? First one, let's say, is that is comes in both forms. So it is human readable, described with UML, and then it can be serialized in machine readable format, which is necessary to have automation of system, what we actually need in smart grids. So what is the modeling process to model this very, very simple grid? We are starting here with the information model, which is description with UML. This is Unified Modeling Language. And with UML, we have classes. Each class represents a model object. Then this class has some attributes that describes this object. And we also establish relations between classes. A class actually can be further serialized. It is, but better is instantiated in some objects. It means now from this class, object will keep the same meaning, the same attribute, but now attributes will have some concrete values, and they will maintain relations between classes. Furthermore, we also have some organizational architecture of these classes that should reflect what we actually see in the real world. In this case, we have different relations, and for instance, here is inheritance. We will provide us some hierarchical architecture in our SIM model. Then, okay, this is the procedure. What does it mean? First, we have information model, which is in UML, which is human readable. This is very nice. And it contains all these models that we need to model processes within power system, also power system components, and so on. And this is these three most important standards, that is standard suites, that together make this canonical model. However, we don't need all these classes and relations which are available in the canonical model to implement one use case. So we reduce our canonical model to the shorter model that contains only classes and relations that we need, which is called the profile or contextual model. And then from this contextual model, we go to the implementational model, which allows a software to generate some files which are instances. For instance, let's say, for example, RDF file that contains a distribution grid model, for example, of the overall distribution grid of one DSO, for instance. Okay. So this is the concept how we are doing it. Then we choose one of these standards, in this case, for our topology, we actually need this IC 61970, which contains all these power system components. And for our simple topology, we have a package. Okay, all classes are organized in some packages, so we can handle it and manage more easily. And when we go and see what is inside the package, we see these classes, which actually helps us to model our very simple grid. For instance, we have AC line segment class, which we need to model our power line, or we have bus bar section to model our bus bar. So we have these components, and each of these classes actually incorporates some semantic descriptions. In this sense, if we are using a class for some purpose, you have to check description and see, and is this class appropriate for your purpose? This is why we have description for each class, and then we have this common understanding of all models. Okay, so we are back to our very simple model. So I identified these classes to model all these components. The question is this enough to make our profile, which will be used to make implementation model and generate some instance files? Unfortunately not. Why? Because SIM has also some rules how you connect elements, how you model the grid. So each of these components actually have terminals, how they connected. For instance, power line has 2 terminals. Generator's got 1 terminal, and then we introducing something what is known as connectivity node. So connectivity node doesn't exist in the real life. However, it is used in our model to link different components into one point. So what are we missing from our previous topology? We are missing this terminal and these connectivity node classes. So now we have all classes we actually need to make our profile. And this is it. So we extract from our canonical model, in this case IEC 61970, all these classes we actually need to model our sample grid. You will notice that there are some classes here, for instance, like this, which are not present on our topology in the previous slide. Why is that? We have this hierarchy and inheritance property in SIM. For instance, you have this AC line segment which inherits from class conductor and equipment so far and so on. Okay, and then if you go to this terminal, for instance, terminal must be somehow related to the AC line segment. So we have to connect it. We need relation between classes AC line segment and the class terminal. This relation is established through the relation which is known as association. So we can say to the AC line segment, we can assign 0 or more terminals. In our case, to the AC line segment, we can assign only 2 line terminals. Another example of such usage of this association are measurements. For instance, let's say you are making some measurements, and these measurements should be written in the file that you are exchanging. So you need a model, for instance, for the voltage measurements. However, it is not enough to send someone a measurement. it is also important that other side knows where at which location this measurement has been taken. For instance, at the secondary terminal of the power transformer X, Y, Z. Okay, so you will assign this class of the measurements to this terminal at the given power transformer. So behind on classes are not only important here, also these relations are very, very important. And in the last slide, I just want to show you how is going this implementation cycle when you want to send someone a grid topology in the SIM XML, for instance, or RDF format. It means that after we defined our physical model, which we want to model, we use SIM canonical model, which is provided in UML. Depending on our use case, we will extract only classes and relations which are important for the information exchange within our use case. It means from extremely large canonical model, we will make SIM profile. It means a reduced model which completely meets the needs of our use case. How we actually do it? There are SIM profiling tools. Usually, what we prefer is to have some graphical interface, and this is software known Enterprise Architect, and then we have different plugins for this software, Enterprise Architect, and we have some rules and make a profile. I'm not going to talk about these rules today. Okay, so we get this profile, and from this SIM profile, we go to the implementation model. What is implementation model? It is XML schema or RDF schema. So XML and RDF file are machine readable files which are appropriate for automation. So then after we have these tools again with an Enterprise Architect different plugins. In our case, we want to generate RDF schema. This is RDFS. And for instance, we can use SIM syntax gen plugin. Okay, so when you have RDFS, this is very, very important for any kind of software. So you can use a kind of framework. For instance, in Java, it is Jena RDF API. And with your input data, you can generate RDF file. So with some rules, and this RDF file, for instance, can carry the model of your electricity grid. Okay, so these RDF files are further used to exchange information, to exchange these grid models, for instance, between TSOs, between TSO and DSO, and so on. However, this is not very useful further to analyze something, to extract some knowledge from such files. So we usually import these RDF files into the databases. So these databases most appropriate for RDF files are triplet databases such as TripleStore or graph databases which natively support RDF. And you will see later why. So after this is, for instance, grid model installed in the database, then we can use different semantic query languages to extract different knowledges. But it's also important that we can, with this approach, also combine different sources to extract a knowledge that we actually need. So at this point, when we have an RDF instance file, how SIM ontology is used to store this data and make a query, This is what Amila is going to talk about. Thank you.
Thank you. I will just go one slide back. Thank you, Nermin. So I'm going to talk now more from the graph database perspective. But before going there, just a quick review. So we're talking about interoperability in smart grid. And our approach is to use a combination of semantic data modeling and graph databases. In regards of semantic data modeling, we are talking about the common information model SIM. You have now heard a lot about it, how it is constructed, and of course it is rather human readable. So it uses UML, which is a pictographic language. That cannot be exchanged, so we have to use another data format. Generate RDF instance files. We have been using the RDF XML serialization. Why? I'll explain it a little bit later. In regards of graph databases, we do not want to exchange or send around these instance files all the time. We would like to store them somewhere and give people credentials to access this data. That way we can fastly change things, upload, download, and so on. And in regards of databases, we've decided to go with graphs. Why? You will see it now. But in regards of that, I would like to say that we've been using two databases. We were using the Neo4j database and the GraphDB database. We've been using two databases because we want to show how different databases, graph databases, are actually handling the SIM ontology and the RDF instance files. Before going into the direction of graph databases, I will just give a brief introduction what RDF is and why we have chosen this instance file instead of XML, for example. RDF is short for Resource Description Framework. It's a directed graph data format, and as such, it's completely in accordance with our idea of using graph databases. It is semantic, it gives us unique identification, so we have everything we need. Also, as you can see in the figure right, RDF is at the base block of the semantic web stack, and as such, it is in compliance with all the more sophisticated or more complicated languages. So that is also a huge plus for RDF. We have chosen the RDF XML serialization because it's the most popular one and most grid data is serialized in this form. Before being able to upload or import an RDF file into a graph database, we have to be familiar with its structure. The structure of RDF is called triple or statement structure. Since the name says triple, it's obvious that it consists of three parts. As you can see here in the figure, we have a subject and an object and a predicate. The subject and object are presented as nodes, while the predicate is a relation between these nodes. Maybe you've noticed that we have here two objects that have a different form. This is due to different kinds of objects. The object can be either a resource or a literal. If it is a resource, it means it can be part of another triple. It has an ID and it can be further used. If it's a literal, it means that it's some kind of primitive value, for example, an integer or a string, and there's no further going from there. It is usually presented in that way that if it's a resource, we use a circle, and if it is a literal, we use rather a square form. So now that we're familiar with how RDF looks like, we can take a look at how an RDF file looks with following SIM ontology. So here we have just a small segment from a real grid model. You have already seen this kind of enterprise architect presentation of classes in Nermin's presentation. So we have two classes. We have position point class with two attributes called X position and Y position. And we have one class called location, which at this moment has no attributes. We have also a relation between them that is directed. This is very important for RDF. You cannot generate an RDF with undirected relations. All relations have to be directed. So as you can see from the real grid model, the small segment, that we have different tags. This is only one element. Of course, a real RDF would be consisted of many, many elements. So here, the first tag is only about namespaces. This defines where, for example, we can find more information. This is the semantic part. The second tag is the large tag, is actually our element. You can see that I have kind of put the colors to be able to follow this RDF form. So SIM position point is actually our subject. And you can see here in the graph that we have the circle is red, and that is, of course, our subject. Then we have to find the object and the predicate. Here in TIM, the attributes in RDF are actually predicates, or the name of the attribute is going to be a predicate in the RDF. So we have here two attributes, so we have two predicates. We have the X position and Y position as predicates. Since these values are primitives, we're going to have literal objects, and these are going to be shown as a square. So for example, for the X position, we have some kind of number, and for Y position, we have a number. The third inner tag is the new relation. Here, as you can see, we do not have any primitive values, but we have actually an ID. This ID says, okay, it's going to be a resource object, so I have to create a predicate towards a resource object, so a circle. And this object, you can actually find it further on as a new element because it's going to be part of other relations as well. So this is how you go from the TIM UML presentation of classes to an RDF presentation of classes. As you can see, it seems a little more complicated. The graph is more complex because now attributes have to be treated as objects and they're not just inside a class anymore. Now that we kind of understand how RDF is constructed, we can actually take a look at graph databases. Why did we choose graph databases? First of all, graph database is a database as any other, but it's not consistent of tables, but it consists of nodes and edges. So now data is written inside of these nodes and relations, and that's how we read it. Of course, we have different types of graph databases. Usually the classification is done based on the base model. For example, is it a labeled property graph, or is it some kind of triple or a hypergraph? Or it can be also done, the classification can be done based on how the graph database is looking through, searching. Is it using indexes or is it index-free? The two databases we have been focusing on are Neo4j and GraphDB. We have chosen these two because of the reason how different they are. Neo4j is a labeled property graph database. So that's a database just as you imagine it. It has nodes, it has relations, it also has labels, which gives it a little more sophisticated look compared to the simple mathematical graph. GraphDB, on the other hand, is kind of a compromise between a graph database and a triple store. So we have all those nodes and relations, but they're all constructed in the way triples work. So we have the subject predicate object for it here consistent. And that is why GraphDB is RDF native. So there's no problem with importing RDF. We don't need any special plugins, anything. We just use the workbench, import it, and it's all going to be parsed in the right way. On the other hand, Neo4j as a labeled property graph database is not RDF native, so we have to use some kind of plugin to import it or develop our own. Neo4j offers the Neosemantics plugin, but we have also tried developing our own using Java, and we called it the TIM ontology-based adapter. Both of them imported it fine. The only difference is that later on your RDF is going to be treated as a labeled property graph. So there's not going to be no special treatment because it's RDF. It's going to be treated just as any other graph. The searching is also different. Neo4j uses index-free adjacency, while GraphDB is using the index lookup method. The languages for querying are also different. Neo4j has its own developed Cypher querying language. GraphDB uses the standardized Sparkle querying language. Below the table, you can see two figures. This is how a substation element looks in both of these databases. As you can see, it's very similar. Ignore the colors, just look at the structure. The predicates are the same, or the relations are the same. But as you can see, Neo4j has in the nodes written the label. So it's also obviously rather label-oriented, while GraphDB uses IDs, which is also kind of an RDF thing. So this is more maybe the biggest difference, but all the other things are kind of similar. So this is how they look like, and this is how their querying languages look like. I thought it's important to mention this as well, just to get a feeling maybe which database would be more of your type. As you can see, Cypher is maybe more SQL-like. So you have clauses like match and return, and it's also rather descriptive when writing queries. For example, here with match, we are describing the path from substation to position point, and then we return the desired values. For example, X position, Y position, and the name of the object. On the other hand, Sparkle is organized just as and triples are organized. So it's writing the queries as if it's writing an RDF. You have the prefix definition, you use select to define what you're looking for, and you use where to define where to find it. So this is kind of the difference. For someone who's coming from the semantics world, Sparkle is probably going to be the choice, while for someone who is coming from the world of SQL and databases, maybe Cypher would be easier to follow. Now that we know the differences and we understand the querying languages, we can go and see how these perform. For the performance analysis, we have developed a simple use case. In this use case, we were using two real data sets. One is a smaller model that has around 3,000 nodes, and we have a large model that has roughly 6 million nodes. In this use case, we have three main steps. The first one is that we import our models into both databases, both the small one and the large one. Then we retrieve all substation and AC line segment information. And finally, we generate a KML from this information, import it into Google Earth, and visualize our grid. I have to say that both databases did this use case fine, and the figure in Google Earth in the end was the same. But what about the performance? The performance analysis was done based on the most popular key performance indicator. We used different studies and found out, for example, that the most popular or mostly used key performance indicator is the query processing time. So this is the one we're going to focus on today as well. For this analysis, we went through three approaches. Our first approach was maybe the first one anyone would go to. That's the iterative procedure on the original dataset. We have our dataset, we didn't change anything, and we went query per query through elements with smaller queries through all elements in a loop. As you can see in these graphs, this is a time graph. So it shows how long each query needed in a sequence. The first query in Neo4j needed the longest time. This is because it uses index-free adjacency. It scans through the entire network, and then it takes, of course, the longest for the first time. Then it goes node per node and looks through its neighbors, so the time drops. On the other hand, GraphDB has index-free adjacency. That's we have some kind of random peaks, and we can't find really a pattern. Also for this is for the smaller model. And as you can see already here, Neo4j needs around 30 milliseconds is the highest time, while GraphDB needs around 0.1 millisecond. For the small model, this seemed fine, but when we tried it on the large model, Neo4j needed 11 hours, while GraphDB needs 6 minutes. So it was obvious we have to find another approach. So what we tried next is that we did an iterative procedure on the optimized dataset. We found out that our dataset was a little faulty. We had some missing values, we had some duplicate values. So we kind of done some research on the dataset, removed all these values or fixed them, and this is what we got. So the querying time for the first one has dropped, of course, because we have a smaller dataset now, and of course we had less sequences, again because we had less elements. This did do some performance boost. We dropped from 11 hours to 10.5, but that was still way too long. So the third and the kind of revolutionary step was to only use one query. We wrote a query that was big. It took the entire grid at once, or the entire database at once, and needed only around 20 seconds. So for Neo4j, we dropped from 10 hours to 20 seconds for the use case execution time, and GraphDB needed from 6 minutes, only 22 seconds. Maybe you have noticed in the table that the query execution time for Neo4j is way longer than for GraphDB, but the use case execution time kind of seems the same. This is not an error. It is due to the expressiveness of the languages, querying languages. Neo4j has a querying language that is more expressive. We could do lots of things inside of the query, and we didn't need to do further Java code writing. On the other hand, GraphDB has Sparkle, which is a little more simple. In GraphDB, with Sparkle, we could more or less only retrieve the data, and then we had to do all the programming ourselves to get some sorting, ordering, and so on. And that is why, in the end, the use case execution time seems kind of the same. But both had an enormous performance boost, and in the end, actually, for the amount of elements, since we had 6 million nodes, seemed fine. To conclude, both databases could support our use case, and both of them were adequate in the end for storing our TIM RDF files. We have realized that TIM was more expressive, but on the other hand, Sparkle was RDF native. Sparkle is also standardized, and it's obvious that standardization is a huge step towards interoperability. So that might be a kind of a little plus for Sparkle and GraphDB. But most importantly, semantic models stored in graph databases did improve data interoperability. We used TIM, first of all, that's a big thing. And then secondly, we have used databases for storing our data. That way, we didn't need to have to send around our files. We didn't have to always update and send around new versions simply because one little element was changed. But it was enough just to do all these updates inside of the database. And also it was a security improvements because all we did is that we would give credentials to those users to access parts of the database. Those who don't have the rights wouldn't get it. So we are definitely still going to research in the direction of the combination of semantic data modeling and graph databases. Thank you.
Thank you, Amila. As promised, we did it in 44 minutes, not 45. Okay. Thank you for listening. And now we have 15 minutes and we are available for your questions. You can type a question, you can raise your hand if you want to ask, because we don't have any question in chat. At this moment, we can have a discussion. It's not necessary to write a question, okay? Okay, so I cannot see any raised hands.
Zdravik Vitek, I have a question.
Okay.
Have you considered, for example, Stardog? It means, have you considered also the others Sparkle databases as Stardog, and have you compared them?
No, actually, in this in this work, we just focused how we can combine the SIM ontology, RDF with the graph databases. Okay.
Okay, thank you.
Okay, and another thing I just want to, when you open this stuff, this comment, when we are deciding about the Cipher, the Sparkle, we also investigated, can we make an adapter between these two? Because many resources are available on the internet, on the semantic web, and the Sparkle is quite useful. Okay, and this is why they usually prefer Sparkle here. But Cipher is for Neo4j. Okay. What is it, Victor? Did you have to implement any extensions from IEC standard models? No, this was completely according to the IEC 61970. So about this, about these models, and we use these already. These are real data. This is actual data, and took a model from the actual distribution grid. What was observation actually that we need also, we had some redundancy and some bad data in this instance file, and before the storing also from RDF in such cases we can recommend, let's say, Amila, I'm right, to clean up the data before storing into a database. Okay, question by Nikolowski. Okay, just one. As I understood, query execution time in Neo4j was significantly improved because of data cleaning, data imputation, database optimization. Amila, are you going to take that, or?
Yes, I can take it. Actually, we managed to improve it around the 30 minutes. So it was not significantly improved. It was improved, But the significant improvement was a result of us changing our query way. So instead of working with for loops and doing many small queries, we've decided to use only one query to query the entire database. So that was the significant improvement. The cleaning is certainly good. You definitely should be done. But in this case, it did not bring us that much of a result. But as I said, it's definitely recommended to clean your data before storing it anyway.
Okay, thank you. How about this? How does SIM versions affect your work? I know that SIM is not a version of SIM anymore. Yeah, this is true. SIM is quite evolving, changing a lot during the time, and actually, it affects like other stuff. It is even better when we are using these databases because of this semantic meaning. If you remember this, how everything in the Matthäus, the first part, the last slide, what was presented. Now we still have a meaning, and from this database we can also serialize in RDF in a newer version of SIM to understand. But it is always important that we agree that we know which version of SIM we are using. This is the only important thing. Hopefully I answered. Okay. 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 About this is this is excellent, great question about the learning curve. This is about the SIM. SIM is quite extensive, and you need various knowledge actually. But if you are guided, this learning time can be significantly reduced, because you need some prior knowledge about the modeling, about UML, to understand this stuff, to understand the rules, and then you can understand the standards. And it is also at the end a little bit how about these ICT architectures, how we exchange information, but it comes on the top at the end. But let's say it takes time. You need various knowledge, but when you start working, it's very much doable. And this is why I took only this very simple example to show, okay, how we can do it. And the step by step, if you get understanding, which is quite good, then it is not very difficult. And of course, you need some hands-on experience with tools. Okay.
Yeah, and a small recommendation is when working, for example, in the database, you should have maybe your enterprise architect always opened, or wherever you're using your SIM. Simply to always check, you can never know the entire SIM by, in your head, have all the entire SIM. But it's good to always switch around and just get a feeling about how your classes are connected in SIM, in the, for example, canonical model, and then go back to your database. That way, it's also going to be easier to write queries later on. So it's kind of a process of constant, continuous learning.
Yes. And about this, Soren's questions about SIM, it is maybe a buzzword. We said the semantic comparability, the semantic modeling. This is the key, because when you have you need for any data warehouse, any kind of data storage, you need understanding of data, and this is the key, because it is a common ground for all applications, for all systems, that they can understand the data, and then they can store this data in their backend and the way they like, actually. And this is good. So it enables this semantic interoperability, and it's common ground for everything. Thank you. Okay, for Mr. Biziak question about this. Okay, this is for TSOs always a question. but there's a solution. This is a network model manager, which actually takes care about that you don't have redundancy in the models, that you have clean models, you're using the same versions, maintaining the versions part. This is a solution, network model manager, and it should be a part of your system. So this is a component which is system responsible for that. Okay, Mohammed, question about this. SIM Contexter is a tool, the most used by EIMV, which is aimed for profiling. Okay, so you make a profile from canonical model using SIM Contexter. Okay, there are other tools like the SIM tool, Mozaurus by EDF, RD. Which are also excellent tools. However, about these SIM syntax generators, the purpose is to generate RDF schema, and this is the aim. So the other functionality. And if you compare with this tool, you use for RDF schema, and with Mozaurus we use to generate XML schema. So these two different implementation models. And just maybe worth of mention is that RDF formats are used mostly for these grid models measurements. And at the end, if you go to XML and you go to market and European style market profile, then you'll see extensive usage of classic XMLs. Okay. Okay, we have 5 more minutes. You're happy to answer if you know the answer. If you don't, we'll come to you later. Okay, so and these are excellent questions. You are painful questions. Actually, we have the standard for distribution grids. Yes, we have working. We are working on for the model for the DSOs. Even though EIMV supports. Extremely supports this SIM for TSOs, and this is why TSOs are extensively using SIM. However, notice also some eDSO efforts also to use a SIM, and we have ongoing standardization on the CDPSM, which is common model for distribution grid. For instance, EIMV provided CGSM, which is a common model for the transmission grid. And then now there's IEC standardization effort for the common model for the distribution grid. However, mainly the majority DSOs implemented some non-standard profiles to model their grids in SIM. And this is some kind of work that should be done to standardize all these profiles and obtain these distribution grid models on the common level. Okay, Sratan, I have a question. What is the main problem identifying distribution common grid model exchange standard, and where is to be expected a unified model distribution such as CGMS for transmission? This is again quite difficult problem. CGMS actually doesn't support this unsymmetrical models. So you have these asymmetries in the distribution grid, and this is the major problem here. So you need a model that will in the distribution grid. You need a 3-phase model, especially in the low voltage grid. And CGMS doesn't support this. However, also when we talk about the TSO-DSO observability area, so in one part of the grid should be exchanged between TSO and DSO, and this should be done probably on the with actually CGMS, but this is a high voltage or medium voltage part of the distribution grid, and in that sense, we can say one phase model can be okay here because there's no such asymmetrical situations in the medium voltage grid. So in this case, we can use CGMS. But now this is also standardized, the CDPSM, and it is mostly on the distribution system operators to implement it. This is what are we waiting for. Okay, Sreten, I'm not sure if you are satisfied with the answer. Yes, asymmetries, unsymmetrical network. This is the major characteristic of the low voltage distribution grid, which is a problem and very difficult to model, but doable. Okay. Okay. We have 1 minute for one more question. For the last question. Okay. So if you don't have no more question, I would use this minute that we all switch our cameras on. Who's got the camera? But we can make some photo together, okay? And before I thank you all for joining us here, I'm happy to have you all here. We will upload very soon in the next days. EIMV has a YouTube channel, and this video will be uploaded on the EIMV YouTube channel for you, and we will share this link. Now I just need to stop
the presentation.
Yes. Stop presenting. Okay. So Amila, can you take a shot here?
Yes, I can.
Yeah, nice. And I like Zeynep's hairdress. Okay.
So everyone, cheese.
Thank you, Professor Narmin.
Okay, thank you. Thank you all. And now I have to figure out how to stop recording.
Wait just a second.